Okay, hey folks, picking up where we left off, starting the second half of chapter 7. So this is going to be predominantly qualitative, so conceptual, not a whole lot of math. However, these concepts get kind of weird because now we're dealing with the quantum mechanics world. Okay, so I'm going to start by introducing this Heisenberg Uncertainty Principle, which maybe that's somewhat familiar for you, right? From Breaking Bad, right? The guy's name, he used Heisenberg as the alias. So Heisenberg was a famous quantum mechanicist, and so he said, based on this idea that electrons also act as waves in atoms, there's a fundamental limitation to just how precisely we can know both the position and momentum of an electron at any given time. And there's a famous equation that describes this, and I'll just show it to you just so you can see it. I'm not going to make you do much with this equation. But where is this coming from? Why does he say we can't really know both the position and momentum of an electron at any given time? Well, that comes back to this idea that, remember, we had to adjust the Bohr model, right? So in the Bohr model, it works really well for just hydrogen because we have one electron in each one of those orbits, okay? But as it turns out, when we put more than one electron in these orbits, they interfere with each other, right? Remember when we add waves either constructively or destructively? As it turns out, they interfere with each other, okay? And so these bound electrons, or electrons that are part of an atom, they also have this wave-particle duality, okay? And a result of that ends up being Heisenberg's uncertainty principle. Where now, if I have an electron, let's say I have an electron moving round and round and round a nucleus, okay? So I might know exactly where it is, there it is, but I don't know where it's going, okay? So that's what this equation says. It says if we know its position very precisely, then we don't know where it's going. Or conversely, if I know where that electron is going, I have no idea where it has been. So I'm only talking about this stuff briefly. We could spend an entire semester talking about this stuff. And in fact, that's what I'm going to be doing in the spring, teaching Chem 362 quantum mechanics. So this is really just an introduction, okay? And so now from Heisenberg uncertainty, another famous scientist, Erwin Schrödinger, came along and says, well, because of Heisenberg and the fact that these electrons are behaving as waves, we're going to treat their positions with a probability function. So if we're saying we don't know really where they are, we can say, well, we maybe know most probably where they are, okay? So what we do, we take what's called the wave function psi, that's a Greek letter psi, okay? Oops, I just wrote the letter. I meant to write psi for psi. Okay, so what Schrödinger does is says, well, there's an equation we could come up with that's going to describe the wave properties of these electrons. We call it the wave function. And when you take the wave function squared, psi squared, versus this distance from the nucleus. So now if, for example, on my picture right here, that spot, that's the nucleus. And if I start drawing an arrow out here, I'll say that's my radius, so that's my distance from the nucleus. Then there's some distribution, okay, some probability distribution that says the most likely value is at the top, most likely or most probable, okay? But these other values, right, they say that there is also some finite possibility of finding the electron, okay? So now what happens is, instead of orbits, okay, like these single two-dimensional orbits, they're really like orbitals, okay? And actually this picture of somebody throwing a rock in a lake right there, I think this is actually a really cool picture of how we can think of these orbitals. So right here in the center, let me change, maybe yellow will show up nicely. Okay, so right here in the center, that would be our nucleus, okay? And so someone drops a rock there in the center, and we see these waves start to propagate out, okay? Like, so maybe there's like a distribution there, right? There's like a probability wave. And then here's another probability wave. And here's another probability wave, okay? So what Schrödinger's wave equation is saying is where there's a large peak, like what we said there, there's a likely place of finding the electron. And when there's a small peak, like I'll point to right here, where this starts to drop towards 0, so it's not very likely to find the electron there. Later on, we will call these nodes. We will learn that nodes are regions where there's no chance in hell you're going to find the electron right there. So no probability of finding it right there, okay? So again, we could spend a whole semester describing this stuff, but this is just an introduction for now. And what all of this stems from is the idea that electrons also have wave-particle duality. So we can't really treat them like these orbits. We have to think of them as these three-dimensional shapes that we call an orbital, all right?